derivatives as rates of change. The position of a stone thrown vertically upward with an initial velocity of 64 feet per second from a bridge, which is 96 feet above a river, is given by the position function s of t. So the stone has an initial thrust upward. How high will the stone climb? To answer that, we first ask, when does the stone reach its greatest height? The stone will reach its greatest height right before it begins to descend, or when the velocity changes from being positive to negative. The change from negative to positive occurs when s prime of t is 0. Or, looking at it graphically, it would be where the slope of the line tangent to the graph is 0. Since the derivative gives the slope of the line tangent to the graph, we are looking for where the slope function is equal to 0. So whether you consider the derivative a slope function or a velocity function, we're looking for where the derivative is 0. So starting with our position function, find s prime of t and set it equal to 0. Well, the derivative is negative 32t plus 64. We set that equal to 0 and we get, we solve for t and we get t is equal to 2. So at 2 seconds, what will be the position of the stone? At 2 seconds, the stone reaches its greatest height of 160 feet. With what velocity will the stone strike the river? This also has two pieces. The first question is, like before, when does this occur? When does the stone strike the river? Okay, so when does the stone strike the river? It strikes the river when the position is 0, which we can see occurs at approximately 5 seconds. To get a more accurate time, we're going to use algebra. Unfortunately, this is a quadratic which cannot be factored. I did divide both sides by negative 16, but I still have something that can't be factored. So I use the quadratic formula, and when the dust settles, I get 2 plus or minus square root of 10. So I get two answers. One of the answers is negative, which I ignore. The other answer, though, is positive, and getting an approximation to 2 decimal points, I get 5.16. So at time 5.16, a little bit after 5 seconds, the stone will hit the river, and it will do so with a velocity. Well, let's find out what velocity. Put that time into our velocity function, and I get negative 101.1 feet per second. So the stone will strike the river at about 5 seconds with a velocity of about negative 100 feet per second. All right, we're going to switch gears, talk about economics for a little while. Suppose a company produces X pens. So just pick your favorite number, like maybe 1,000 pens. Each pen, 10 cents for each pen, but you also have a fixed cost of 500. So what is your total cost for producing those 1,000 pens? Well, it's going to be your fixed cost plus 10 cents per pen. So in our example of 1,000, that would be 500 plus another 100, a total cost of 600. So a total cost of $600 to make 1,000 pens. Well, what is that per pen? How many dollars is that per pen? So another way of saying that is, what is the average cost of producing your 1,000 pens? Well, the average cost is just taking your cost function and dividing by the number of pens you produce, and that gives you your average cost dollars per pen. Now, average cost has a particular notation of a bar above the C. That if you see a bar above a cost function, then what that means is you're looking at the average cost. And I rewrote the function so that you can see the fixed cost of 500 is divided by the number of pens. I like that because it kind of shows how the fixed cost is distributed among the pens, and then also every pen is 10 cents. Notice that although the total cost increases, the average cost per pen is decreasing. And so this asks economists to a question. So suppose you've produced your 1,000 pens. What would be the cost of producing just one more? Well, to answer that, economists use what they call a marginal cost function, which is just the derivative of your cost function. So you take your cost function, take the first derivative, and you have what economists call marginal cost. And marginal cost tells you the additional cost of producing just one more item, in our case, one more pen. Let's look at our example. Our cost function for our pens was 500 plus 10 cents per pen. Well, take the derivative. The marginal cost is 10 cents per pen. So total cost is 510 cents per pen. Marginal cost 10 cents per pen. It would cost 10 cents more. If you've produced your 1,000, you have dealt with your fixed cost, you've got your 1,000, you want to make one more pen, it'll be 10 cents. And I bet intuitively you already knew that. Let's look at a slightly more complicated cost function and determine the marginal cost function for this. This cost function is only valid for items, or this model is only valid for items that are under 1,000. The model is not valid after 1,000 items. Find the marginal cost, so just take the derivative, taking the derivative of the cost function, and then simplify. After you simplify, evaluate your marginal cost for both 100 and 900, and then turn the video back on to check your work. For 100, I get a marginal cost of $46 per item, and for 900, I get a marginal cost of $14 per item. So having produced 100 items for this particular cost function, the approximate cost of producing one more item is about 46. If, however, you have produced 900 items, then producing just one more item is only 14, significantly lower. So for this manufacturer producing this item, the marginal cost decreases as the number of items produced increases. And if I show you the graph of marginal cost, you can see that it is a decreasing function. Take care, and I'll see you in the next section.